Newton's law of cooling states that the rate of change in the temperature of an object is proportional to the difference between the object's temperature and the temperature of the surrounding medium. That is, for example, like the room the object is in. Let Y represent the temperature in degrees Fahrenheit of an object in a room whose temperature is kept at a constant 60 degrees. So that is our surrounding medium, that room. If the object cools from 100 degrees to 90 degrees in 10 minutes, how much longer will it take for its temperature to decrease to 80 degrees? So notice the question is asking for how much longer. That's asking for a time value. What is the amount of time? Well, it would be helpful because we're talking about temperature as it relates to time to have an equation that relates temperature and time. Now notice we were given that temperature versus time is changing at a rate. And whenever I see rate, that makes me think of derivative, like d over dt, the derivative with respect to time. So I'm going to need to start by writing a differential equation. So let's start dy dt, where it's the rate of change of the temperature, and they told us that y represents the temperature. So the rate of change of the temperature that they're calling y is dy dt is, there's our equal sign, proportional to, so that's a constant, I usually use k, times the quantity. It's proportional to the difference. A difference is when we subtract two quantities between the object's temperature and the temperature of the surrounding medium. So remember we said that's like the room that it's kept in, and the room is kept at a constant 60 degrees. So we have the temperature of the object, which is heated up, minus the room temperature of 60 degrees. Because the object is hotter, this makes sense that we're doing larger temperature minus smaller temperature, so we have a positive difference. Now because we're talking about temperature in relationship to time, we need to get rid of this derivative, so our equation only deals with y and t, the temperature and the time. So let's start by separating our variables. I have a y expression multiplied decay. I can divide by that y expression and get dy over y minus 60. And then I can leave the constant over here so it's farther away from the y that I'll have to solve for and multiply by dt, k times dt. Now that my variables are separated, I can integrate. And using u substitution, if u is y minus 60, du would only be 1. So we know that that's going to end up just being 1 over u, which makes the natural log of the absolute value of the u expression, y minus 60. And on this side, the antiderivative of k is k times the variable t and our constant of integration added at the end, plus c. Now I'm going to need to solve for y because it's going to be more helpful in order to work with our problem. So to get rid of the natural log, we will exponentiate both sides. Write both sides as the exponent for base e. We do that because those are inverses, and then I've got the absolute value of y minus 60 equals e to the kt plus c. Now, I know that when I take away those absolute values, it's going to mean I have to consider positive or negative of those expressions. So let's rewrite what we can. Y minus 60 equals, now another thing I can rewrite is e to the kt plus c can be e to the kt times e to the c, where e to the c is just a constant. So let's go ahead and multiply the constant times a positive or negative constant, still a constant, and it gives us y minus 60 equals ce to the kt. And finally, adding 60 to both sides leaves us with y equals ce to the kt plus 60. So here is an equation that we can work with that deals with the y, the temperature, and the t, the time. But notice we still have two unknowns, so having temperature and time, or needing time but having temperature, isn't going to be enough information when I still have two unknowns. So let's figure out what those values are by using some given information. Now they told us that the object cools from 100 degrees. So that means at time 0, the temperature is 100 degrees. They also told us that it cools to 90 degrees in 10 minutes. So that means at time 10, the temperature is 90. We'll jot down that information and then we'll use it to find our C and our K. Now taking this equation, let's go ahead and plug in our initial condition where the y is 100, so 100 equals CE to the K times the time, which is 0, and then of course plus 60. Solving, subtracting 60 from both sides leaves us with 40 equals, now K times 0 is 0, so this is CE to the 0, but e to the 0 is 1. So C equals 40. 40 equals C if we leave it in that order. Now I can plug that back into that equation and write what I have. Y equals 40 e to the kt plus 60. Now remember, I'm looking for time and I'm given information about temperature. So time and temperature should be all I need in my equation, or all I have, but I still need K. So let's figure out what K is using that other given value, given order pair. The temperature is 90 equals 40e to the K, T is 10, plus 60. We'll subtract 60 from both sides to give us 30 equals 40e to the, I can write this as 10k, it's a little bit simpler. Divide both sides by 40, divided by 40, divided by 40, 3/4 equals e to the 10k. And to make the e go away, I'll take the natural log of both sides. Natural log of 3/4 equals natural log of e to the 10k, which makes 10k, and then getting k by itself, dividing by 10. Natural log of 3/4 divided by 10. Let's write it as times 1/10. You'll see why that's more useful as we go plug this into our equation now. So again, back to that equation, y equals 40e to the kt. K, now I have this, natural log of 3/4 times 1/10, all of that's my K, times T, and then of course I still have plus 60. Now, I don't need to simplify, but it's quite easy to, so why not? I've got the e with the natural log, that's right there, so I could use that inverse property to bring that down the part that's inside the natural log, the 3/4. So just to make it easier on ourselves, we'll write y equals 40 times 3/4. This part stays in the exponent. 1/10 t is like t over 10, and then of course plus 60. Now, to the question. How much longer will it take for the temperature to decrease to 80 degrees? So now I'm looking for the time when the y equals 80. Let's plug 80 in for the y. 80 equals 40, 3/4 to the t over 10 plus 60. First we subtract 60 from both sides, so 20 equals 40 times 3/4 to the t over 10. Divide both sides by 40, divided by 40, divided by 40. That makes 1/2 equals 3/4 to the t over 10. Now to get the t out of the exponent, we need to take the natural log of both sides, natural log of 1/2, and natural log of 3/4 to the t over 10. I left some room here because that's why I did the natural log, to bring that exponent down as a coefficient using that log property. So then I can divide both sides by the natural log of 3/4. So it's the natural log of 1/2 divided by the natural log of 3/4 equals t over 10, but I can multiply both sides by 10. Now to my calculator, and the t value is approximately 24.094. Now, of course, these units are in minutes. Let's make sure we've answered the question. How much longer will it take for the temperature to decrease to 80 degrees? Aha, so it's already taken 10 minutes to get down to 90 degrees. So how much longer than 10 minutes? We need to do a little bit of subtracting. 24.094 minus 10 makes 14.094 minutes. It actually takes, and I'm going to get rid of this equal because it's in a strange spot. It actually takes 14.094 minutes longer. Now, I don't usually do this, but there's a lot of stuff on my paper here, so I just want you to be sure that that is my answer. It takes 14.094 minutes longer to decrease the temperature to 80 degrees. Thanks for watching.